Well, there you go. Well, here's the thing. I will tell everyone. I mean, on the final is twice as long, and it's 5 questions out of 6. They're not. The questions are no different. Matter of fact, this answer is exactly the same. So, so you have a lot more time. You have a lot more time on the final. So, the 50-minute is.
It's not exactly the best because it's still hard to find. Because most of them just reading them and trying to adjust information into what I thought.
Yeah. So, that's. I mean, I have to say that. Like I always. Someone else brought this up. You know, the thing is, while we would like to be able to give grades on the basis of understanding how much you've learned, what you understand, we can't actually. Maybe in the future we'll be able to do, you know, MRIs and figure out just how much you learned in your head. But we can only test skills of one kind or another, either calculation or writing or reasoning, some programming. Choose a skill and say that's what we use as a stand-in for um, uh, for whether you learn. And it's not absolutely, can't be 100% accurate. You just do our best, try to make it fair and predictable. But I agree. I mean, in some sense, there would be no reason not to have every exam unlimited time. I don't really care how long it takes people to figure stuff out, except then it has to be a take home, and then everyone just get it. So it's a different thing. So it's just limitations. Well, maybe this is something we can talk about at the end. You can put in the writing things. One thing I've never done, but I have considered more. I've gone to the 2 midterm approach. I used to start with just 1 midterm, and decided 2 was better. We could go to quizzes and have more quizzes. If people think that was, you know, it takes more class time is the problem, but then they're not as pressured. So I just want to think about that and give us feedback about that. You can change things up and spread it out. Take another 10, you know, at least another 10% of the class and put it into quizzes in addition to homework. Just take all of that. I mean, it's terrible. Logistics of just doing an exam with 100 students like we did. It's painful, but at the end of the quiz is easier. Learn how to do that. I think that's a good idea. I haven't learned how to use Blackboard other ways, so I could probably do that. You know, they're considering going to a different vendor. I also considered going to multiple choice, which is all this breaking, but yeah. Yeah, so the answer is I don't know. They're figuring that out as we speak. There's some chance that parallel programming won't get taught next year. It's not as required. There's a chance. I don't know.
Courses. Did you
Well, yeah, so just tell the department head you want them to pay more. But I don't quote me that there won't be the class. Like you said, there might be. They have to find someone. The problem is they have so many faculty members, and then the new ones get a lighter teaching load so they can do their research. And then if you bring a lot of money, they give you a lighter teaching load because you have the money and you have to do the contract work. And then there's others left over. Someone goes away for a year. They can, and it's possible. Some departments will hire lecturers. It's very hard to find qualified lecturers in this field, in computer science, computer engineering, who don't have very good paying jobs, somewhere else. So sometimes you can. Okay. If I find out, if I hear anything more about that, I'll let you know about it. So yeah, they knew I might have been leaving, so they put me on all these courses that were elective CS361 both semesters. In my own one.
Are you leaving?
Sorry?
Are you leaving?
Next year, 1 year. I'm in Kenya, and I got a Fulbright scholarship. So
What?
I got a Fulbright scholarship to go to Kenya. Yes. So, but I'll be back. What was my other course? Oh, it was parallel programming networking. So there are a lot of people who work anytime. So yeah. Right, that's the graduate operating. Who teaches that? Charles. Next to mine. CE professor. Yeah. That course 560 is not hands-on either. It's all based on papers. It's a project. It's not serious. It's not a. At one time, Dr. Plank taught it, and it was like make your ears bleed. Real operating system implementation, but on a simulator. But no, it's not. Okay, so we're going to forge ahead. Now I have to say, we had a little interruption there with the review and the exam, but I just want to reiterate, this area we're getting into now, I consider one of the really kind of, what's the right word? I find it kind of, maybe, I'm loath to say I find it exciting, because that sounds a little pathetic, and I find the architecture exciting, but it is. It is because of the fact that it is complex and kind of tricky in terms of what it's doing, and it does so much and kind of unexpectedly for the core operating systems. So I really just kind of like it right in there with context switching and multitasking, the way that works. So other than, I consider this, there's multitasking, which is clearly one of the major things that operating systems do for us and create the environment that we work in by giving us the appearance of parallelism even beyond what may be there in multi-core. And then there's a bunch of these other management. Then there's synchronization, which is trying to overcome race conditions and creating good parallelism, okay, and concurrency. But then there's this area. And this area is memory. And the thing about memory is it is the other big area of sort of the sandbox of what an application program sees, what you have been using all your programming up till now. You have an address space programming in C. You can use pointers and see the address space pretty directly. You're a higher level language, even so, you've got variables, local, global, heap. It's all just kind of there. And we discussed a little bit the fact, okay, that we have the physical, just to back up a little bit, the physical memory over here. We have then the virtual view of that memory, which is not quite the same, but in the mechanisms we've seen so far, it's almost the same as the physical view. We started out just by constraining it, so you can't. We use that relocation to enable us to swap, to move it to disk and move it back. I don't know if I emphasized this. Why is relocation important to swapping? Swapping has to do with the disk. So why is it only once we have relocation that we can effectively do swapping? Okay, I'll show you. Let's go back to relocation. Good thing to review before we press on. So this is relocation of the virtual memory space, so you don't have to be exactly where so you add the relocation register to it. So swapping means we can take the contents of memory, move it to disk, move it back, but we have to have the relocation register in order to effectively do that.
Might not be putting it back in the same spot.
Exactly. You need the flexibility. The relocation register enables you not only to put the address somewhere other than in physical memory, other than where it is in virtual memory, give you an offset, but it allows you to change it. You can move your process in physical address space without affecting the virtual address space at all. Okay? So that is really important about relocation. It adds a level of indirection. Okay? If you just do the checking, you're not really adding another level of indirection. Here, that relocation register really holds a pointer to the address of the beginning of the address space in the physical address space. It's a pointer. So that's redirection, indirection we have here. And so that indirection allows us to move if we want to compress, if one process ends and we want to compress the address spaces in order to get a big free space, you can do it using the relocation register. Process is unaffected. Okay? You can move it all the way to disk. So for a while, that process has no physical address space, but when you move it back in, you need to allocate somewhere and just put that value into the relocation register. So this is already, even though it's a very simple mechanism, it's pretty powerful because it enables us to do a service, namely moving things to disk and back, or move them around in memory without any effect that can be seen within the sandbox.
Kind of how scheduling is, you take something out of the concept, you kind of put it back in, kind of like that.
Well, this is a little different. I mean, it's related to scheduling because if something is not runnable, then you might want to move it to disk. That's one thing. Or, yeah, I mean, that's really the only relationship to scheduling. The thing is, scheduling has to do with multitasking, which process or thread runs at any time. This has to do, so that's sort of, you can think of how we share the computational resource, CPU. This is about storage and memory. It's about how we share the memory resource among a large set. So it's not really the same. And we have scheduling algorithms, which we studied. Okay. Policy, different memory algorithms implement different policy. Well, guess what? We need policies here also. What policy do we need in a swapping environment? What decisions do we have to make?
Choose which one to swap out.
Exactly. Which process is the best to swap out? And you could prove, actually, it's not too hard to prove, that the one you want to swap out is the one that is going to not be runnable for the longest period of time. Okay, the one that will, and very similar to shortest job first, kind of the opposite. And again, you don't really know when a job is going to become runnable, so that's not, but you can estimate. You can try to estimate. So it's analogous. They're analogies, but they're different mechanisms and for different resources and different specific policies. So we have this swapping, and then we have the question of what kind of mapping we have from the virtual address space to the physical. It's a very simple mapping I've described so far. It's an offset. One value you add to the virtual memory to give you the physical memory, and it gives you a kind of allocation of the physical address space, which is very simple and kind of limited, because it has to be the entire virtual address space is one big contiguous chunk from 0 to some number or some zero some number, and it goes in one contiguous chunk in the physical address space, starting at some point and going until the end. So it's just a movement of the entire thing. It has to be one big piece, and it goes as one big piece into the physical address space, just somewhere else. Okay? So that's not really how we tend to use memory, because it's not the way it's not the most convenient way. It's convenient to have memory to have at least two partitions, the most basic kind of way of structuring memory. One partition down at low memory, one up in high memory. Usually we use the low memory for the code and the data segment. So the sort of traditional, before modern computers, that was all the memory, that was the contiguous piece. We like to put the stack up at the top so it can grow down. So you can have the stack, if it's going to grow down into the space between these two pieces, right? So that's the way we usually do things. Big contiguous chunk at the bottom, it doesn't change. A growable stack up at the top, and then empty space in between, so that if you have a bad pointer from the data space that's miscalculated, it ends up in between, we get an error. How important is it that we get an error? Pretty important, right? Pretty important. Here's an anecdote which I think is helpful in terms of remembering that, right? So you want error. If you do something wrong, you want to get an error. If you overflow the stack, you don't want to write the stack next to it. Okay? You want to get an error, which is why we like having a separate stack segment, so that we can have space next to the top of the stack, and if you overflow, you can get an error if you miscalculate. So that's how we like to do things. In the computers where C was originally developed, which C was developed for, the PP11, and those machines from the Digital Equipment Corporation, it was common, and in many architectures it was at the time, it still is common, not to start the address space at 0. Okay? You started maybe at hex 1000 or something. Some at least one page, we'll get to pages in a minute, but some piece is left actually unallocated at 0. And sometimes it's used for things like I/O, because of the way that the memory and I/O architectures work together on those machines. They have a single bus, so you could use low memory addresses as I/O, that kind of thing. So you would have even in virtual memory, that would be in physical memory, the I/O would be in virtual memory, you would still leave the bottom unallocated. Then you'd have code and data, then stack. And for that reason, the null pointer was 0. And if you tried to dereference the null pointer, you ever had that experience? I think at this point, maybe, yes. Dereference the null pointer, you get an error. Okay. But that is an odd thing because it's architectural. And in fact, someone, I forget which vendor, came up with a machine that they were going to run Unix on, and they changed that. They said, why? That's just a strange thing left over from, let's allow allocation of memory right down to 0, and they made Unix do that. Allocate all the way to 0. Well, I had this irregularity, which meant, what was the consequence? Right, if you well, specifically, out of bounds of memory, you're never sure if you've got a bad point. You could point somewhere that you don't intend. But the null pointer is awfully important. It's a special case, right? And people dereference the null pointer more than anything else. And if 0 was actually a memory location, dereferencing the null pointer would not create an error. So suddenly, dereferencing the null pointer, while still an error, did not create a segmentation fault or a memory fault. Okay, and it was terrible. It was just you couldn't teach C because people couldn't figure out, so they actually had to go and change their version of Unix to not use that, even though they could, because getting the error was important. You look at me like I'm crazy. Does it make sense to you? Yeah.
Oh, yeah, it makes sense.
Okay, it is a little odd, because you have to make sure, in this case, that errors occur when they're needed. So and in the case of overflowing the stack, you can't make, with pointers there's no way to guarantee you'll always get errors, but you want to get as many errors as you can when there are miscalculations of pointers. So that was that architecture, and so they had to go back and redo that. Okay, so at least 2 partitions for user processes is important. Well, let me say, in the contiguous case, every process is one big piece, and that's what we don't like because of the limitations, but that is a simple case. So again, the kind of hardware that we can have, just expanding a little bit on the relocation register, is to have relocation, which moves where the base of the virtual address space where 0 would be mapped to, and a limit register that tells you what the highest one is. So that gives you a piece, a contiguous piece that now is a sandbox. It's a simple sandbox, a rectangular one, not a bad choice for sandbox, but it's not 2 pieces or anything like that. And so this, I think it's important to forget about these mechanisms that we're flashing up here. This is hardware which happens on every read and write. This is part of the memory management unit or the memory interface. It's simple. When it gets more complicated, you need a whole unit to do it within the CPU. But CPU generates an address, it gets checked, you add to it. This happens as part of every load and every store. Okay? It's not a whole lot of work. And the add is a simple add, all happens in one cycle. You don't have to add any cycles just for this. And then we go to memory. But it's getting more complex. It's more complex than just sending the address to the memory. It's going through some hardware here. And with the possibility of generating a track if it's too high. So in this picture, we're starting at virtual 0 in this picture because we just have one big piece. Next, we'll get to how we can separate out the partitions. Okay. The first thing to do is to make it so that you can have multiple processes. Okay. And the idea there is that you want to allocate the space. You want to make room for multiple processes. Instead of having just one process that you boxed off and mapped to physical somewhere, we want to be able to have multiple processes in physical memory, and that's going to enable us then to run them one at a time by choosing which base and relocation register to load in and make a sandbox. Run a few at a time if we have multiple cores by choosing a few and loading their base and registers, relocation and limit registers, into one of those pairs of values into each core. One word. So when I was presenting contexts for processes before, I was pretty vague about what the virtual memory view was and how it was implemented. And the reason for that is because there are different ways of doing it. So here we're getting specific. So before, what I taught was the virtual memory view is either in the process status register or pointed to by the process status register. That's sometimes true. In this case, it's two values, right? So there's probably two separate registers, not part of the PSR. The relocation register and the base register. And that is what is loaded and unloaded in the context. But we'll see there are a number of different kinds of data structures that are used. That's a very simple, just two values. Okay, so you have two registers. In some cases, we have a whole data structure that's actually stored in memory. We'll get to that. Then you might have a pointer to PSR. So that's why I was vague about it. The important thing is it is either part of or all of a small number of registers that determines the virtual memory view. It's stored, those registers stored in the task control block, loaded from the task control block. That's always true. Okay, so the idea now is even without getting each process is still just a rectangle, just a contiguous piece at this point, but we have multiple processes to deal with, and you can do things with them. You can move them around in order to get different sizes available. It's very much like malloc. There are fewer of them and they're bigger than most malloc, but that's how things work. Any process then that is part of the system at all is either going to be loaded into physical memory somewhere, or it could be on disk. Right? That's the choice. If, just to go back a little bit to the policy point, suppose we have a big process, big-ish process, we move it to the disk in swapping, then we have other processes that we give its memory to, right? We allocate that memory to other processes. And then that process we put on disk becomes runnable. Get some input, whatever, something happens, it becomes runnable. And there's no room for it in memory. There's no hole big enough to put it in. We can't run it until it's in memory. Right? So then our policy has to tell us, has to identify victims. Yes?
You've got relocation registers.
Yeah.
Couldn't you compact the physical memory?
I would say only if the total free space is big enough.
Yeah.
So you could try doing that, but suppose you do that, you compact, or you just look at it and you say, even if I compact it, it's not going to be enough space, right? We just calculate that. So that would be maybe option number one, might be to compact the space. But if that doesn't work, then you need to identify victims, processes to write out. And at that point, actually, it's possible that all the processes are runnable. Can't find waiting processes, enough of them to write out to make space for the one you want to bring in which case you got no choice, either to leave that runnable process, the one that just became runnable, leave it on disk or move other runnable processes to disk. So with swapping, you can find yourself, if you really are kind of very full, in a situation where you have not only waiting, but even runnable processes on the disk. you decide which one is the best choice. If you really overload your system and you have a bunch of runaway processes, some of them which on the disk, things can get bad. Things can get very slow.
This is where like a priority person come in.
Priority helps here, right? Yeah. But you know, that's yeah. So we have various kinds of scheduling things to try to get us through that, but it can be bad.
You have to have like some sort of policy for how you deal with how you deal with moving big chunks in and out from the little chunks, and how you create coalesce free and mine out that.
Exactly.
Coalesce.
Right. So you need mechanisms to try to do things like coalescing. Then you need a policy, because even coalescing these things takes time. So if and then you need policies to figure out, oh, if we can't coalesce and get the space, which ones to move, which ones to write to this, all of that. Yeah. So it's not terrible, but it's a bit of it's somewhat complicated to do all of that. And usually what you do is you sort of prioritize the consideration one thing at a time. Right. So we have these kinds of approaches to finding space for a process. First fit, best fit, worst fit, very much like malloc. Same kind of thing as you do for in a single process on the heap, right? Only it's now in this context of allocating these larger chunks inside the physical memory of the kernel. So is everyone at this point? See, this is where it's nice at 360 word prerequisite. Is everyone familiar with these strategies? Anyone? I can go over them in more detail, but I'm assuming everyone. At this point, it's on the book too. But these are the same kind of policy considerations as malloc. Okay, so as with malloc, then we have these kinds of considerations of fragmentation. Two notions of fragmentation. External fragmentation, where, as was suggested, we have enough room for an allocation we need to make, but it is not all in one big piece. And so you have to, but when you don't have to, you have the option of moving things around, reorganizing in order to get. But that takes time. And if you're not doing that, then then you may lose access to that space until you do, or until so fragmentation can increase and decrease as things are allocated and deallocated. And then there's the internal fragmentation, which is the data structures of the heap or a list or whatever is used to keep track of the free areas of space. That's all space that it's actually you need to keep track of both the free and the used areas. And so it's an overhead for that allocation. Also, we allocate memory in terms of blocks. We don't actually do it on a per byte basis. All of these pointers, the relocation pointer and pointers we're going to talk about coming up, are all on the basis of blocks, which is just a fixed size piece of memory. Early architectures, it was 512K, 512 kilobytes, I'm sorry, 512 bytes, 512 bytes, half a K as a block, perhaps. That increased to a K, to several, 4, it's always a factor of power 2 because it's a prefix on the pointer. I'm not actually sure what current architectures do. I want to say 8K, but it's a piece of And by using those blocks, it means you can save some bits on all the pointers that we're gonna use. So it makes them shorter, that's the basic thing, and it means the hardware, doesn't need to carry the low order bits around everywhere. So it actually saves more hardware consideration than a software. So that gives you a kind of fragmentation, which is if you ask for half a block, you get a block allocated. You have to start on a block boundary, end on a block boundary. So that gives us some flexibility to allocate a contiguous piece of memory, one contiguous piece of memory, put it anywhere in physical memory, and load it, make it just the whole sandbox by loading in those two values, base and size, essentially, into the memory management registers. Fine, we can have a rectangular square box, rectangular sandbox, if you will. But we want, and I alluded to, we want at least two such rectangles, one low memory for the statically allocated areas, one high memory for the disk that can grow over time, stack that can grow over time. And truthfully, even that rectangular chunk in low memory, we would like to segment it into a code area and a data area so that we can make the code area read-only, which is useful for caching purposes and other management purposes. That's something we'd like to do. So we'd like to have two perhaps rectangular areas there in the low memory. So that's already three we've got. Then we're going to want a heap, which we put right in the space between that static data area and the stack. We choose something, a lot of space, so 32-bit architecture. 64 is like all space. So you just choose a place and put it there. Now we got 4 rectangles. If we do something wild like Alec asked the operating system for shared memory, it's going to have to grab a chunk of the address space to put that shared memory in, separate from your own data space or stack. It's another area, another rectangle somewhere that's managed differently, again, for a shared memory segment. These are all things we'll talk about how they're implemented. We've just motioned at them. Open a file, you open a file, but there's a way of opening a file which maps it into your address space instead of giving you a file descriptor to do reads and writes on. We'll talk about how that's implemented, but it takes another area of the end. So you already have maybe easily 6 different rectangles making up your address space, all managed differently by the operating system. So how are we going to do that? We can't easily do that with one big piece. So instead, we say, well, how about having a set of pieces? A set of individual rectangles, which we call segments. Okay, and then what is that going to mean? It means for each segment, we need to have a pair of registers, a base register and a length. And map it to somewhere in the physical address space, and have the operating system. So here are all, again, some various kinds of things that we can put in individual segments. So this was an early sort of next step after contiguous allocation, was to think of the address space as this collection of rectangles. It's a collection because we don't really care what the relationship one to the other is in the linear address space, although they are implemented all embedded in one linear virtual address space. But from the utilization point of view, they're separated out by function, by what they do. So let's say user space is the set of segments, although again, actually looks a lot like physical address space, only the segments give you in different places, right? But the point is, we can move segments around just like we can move processes around. So a process now has gone from a single piece to all of these smaller pieces that are not contiguous and are connected only by the operating system. They all are in a single data structure, which is maintained by the operating system and interpreted. Picture? Yes, here. I'll go back. See that segment table there? Okay, is maintained by the operating system in the kernel. Kernel does this. Okay, and there's a set of limited base registers for every segment. A virtual address now has a segment number, which is indexed into that segment table, which gets you out the limit and the offset, and then the offset to from that base. Okay, so there's the segment number and then the offset D, which you add in after checking. Yes.
So does the program still see just a contiguous chunk like this?
No. I mean, if you think about it, those base registers, the base registers are arbitrary. So in fact, if you do it badly, not only are they arbitrary, so they can be anywhere in the virtual address space, they could even overlap, which would be a mess. So the operating system has to be careful. But there are really no restrictions here, as long as it's just a mechanism. So as long as whatever the operating system sets up, it's gonna. But you never make them overlap because that messes up the cache and other things. They have two physical locations with the same virtual address and the same process. But still, you can put them anywhere you want. So that SD pair there, I want to emphasize, that's a virtual address. If you have a 32-bit address space, usually that SD pair will be 32 bits, and this over here is also 32 bits, but it's not necessary. You could have a 32-bit address here, and you could have a bigger physical memory space, and this will allow you to map your different segments to different places within that physical address space. So, for instance, in the transition from 16 to 32-bit architectures, there was a time when virtual addresses were still 16 bits, but physical addresses went to 32. Okay, first, because it was easy to build a big memory, easier than to build a whole processor that had all the data paths 32 bits long. And then eventually, the processor technology was about a year or two caught up. So we went from 16/32-bit architectures to true 32-bit architectures. And the same kind of thing happened with 32 and 64. So the thing I want to emphasize here, though, is so that SD pair is the virtual address space. That's what your programs deal with as pointers, as addresses. Okay. Here is the physical address that it gets translated to. That segment table is in memory. Okay, it's in memory. So that means on every read and every write, somehow we've got to do a lookup in that table. Now here's the thing. If we build it, it's not too big. We can build it as a set of registers. In which case you can see we could do this all in one cycle. But the next step is going to be something where that table is too big to go into the MMU as a set of registers, and it has to be in memory. So so for now, I guess for this class, think of this as just a big set of registers. so that you can do all of this in one cycle. But keep in mind, we're making each memory operation more and more heavyweight as we go along. Yeah.
Is the segment table on a per process basis or for all the processes?
No, it's per process.
So it's like part of the context of the process.
Well, that's right, yeah. So if those are in the MNU, you've got to load it for every time you do a context switch. If it's in memory, you've got to load a pointer to it into some place like the DSR. Two different ways. But yes, I mean, again, that's architecture dependent. You could have a register with multiple, an architecture with multiple segment tables. And then you would have to manage that set. That's kind of like multiple cores, but they're not executed, just contexts that can remain loaded. So it is an architecture dependent thing. And there have been, at this point, this was sort of a phase in the development of memory systems. There was a phase where in order to make it less expensive to do switching, we started building more hardware contexts, so that you would leave several processes have their hardware context in hardware at once, and you don't have to switch every time. But even so, when you switch beyond the number that can be held at once, then you do have to start a fan. So all of this means one way or another, perhaps every read and write gets heavyweight, and depending on how it's implemented, and perhaps context switches become heavyweight. Now, how many segments was it? I don't even know what the limit is, but it would be a number like 8, right? So it would be maybe 8 set of registers generally, but it's just getting bigger. Again, if you think about it, think of a context as the user level registers, the PSR. Now here's more. It has to be stored and restored. So this assumption here in this is that we have the segment table in memory. Okay, I skipped past that. So that means we need a register that holds a pointer to it. So your question about context switching, what has to be changed is the STBR and something that tells you how many segments there are, how big that table is. 2 registers then have to be switched every time to represent the table. But now, again, we've got to read that table on every read of every write in order to do the translation. And also, it doesn't actually show it. Because there's a segment table length register, we actually have to check S before we use it. Okay, to make sure it's not an illegal segment. That's why we have such a thing as a segmentation error as opposed to an illegal address. Segmentation error started out, at least specifically, an error that said S, the value of S here was inappropriate, was pointing you to a segment that didn't exist, or if the table says that the segment is read-only, it can try to write to it. That's also a segmentation. So those certain things are some of the earliest kinds of memory management errors, other than going to an illegal address. And so you have to check those. And that check is shown here, but I didn't put them on the picture. For some reason. And just the last slide, right, protection, and then putting the protection, the table gives us a place to put metadata, information about the memory, like is it readable, is it writable on a per segment basis. So if you put it there, it's pretty easy to check it during the process of translation. That's when it gets checked. And so that's the functionality for a good long time. This was what what virtual memory was, it's actually not bad. Pretty, as far as creating processes with multiple segments that do different things, you want to manage different ways, it's pretty good. But not good enough. Next time, we'll start in on paging. Paging is what essentially allows you to use memory as a flexible mechanism for creating services of many different kinds, because it's finer grained.